All right, so we're going to continue our lecture with the final chapter of our course. Okay, so for this final chapter, all right. So for this final chapter, the topics, if we refer to the course information, the topics for this chapter 6 will be filter system design or filter design. Okay, filter design. So basically, chapter 6 will be divided into two parts, two main parts. The first one will be lecture 19, which will be discussing about the Butterworth filter. Yeah, this we're going to cover today. And the second part of chapter 6 will be on Chubacha filters. Yeah. Okay, so we are going to actually cover two filter types. Yeah, two filter types which have been designed. Yeah, which are called the Butterworth filter and Chubacha filter. So these two filter type will be our main discussion. Yeah, for chapter 6. All right. So let us proceed with the lecture 19 now. Right. So this is based on our CI. The things to be covered in chapter 6 will be on the Fourier analysis, okay, for the CT system or continuous time system and the filter design. So as I mentioned before, we're going to have a look at two main filter types, which are the Butterworth and the Chebachev filters. Yeah. Okay. So I believe that you have tried to view. Yeah, you have tried to view the slides or the videos on lecture 16 and lecture 17. Okay, so lecture 16 basically covered the topics of boat diagram, yeah, sketching the boat diagram. Okay, I believe that you have tried to at least try to view these videos, okay, and you have, I believe you have understand how to sketch the boat diagram if our transfer function consists of a combination of a constant, zeros at origin, poles at origin, real poles, real origin, and so on. Yeah. Okay. So I believe that you have understand about these issues. Okay. In lecture 16. Okay. And in lecture 17, we have learned about the filter type. Yeah, filter type. Starting from the low pass filter. So basically, we have learned about two filter type for the first order type, which are the low pass filter and the high pass filter. And we have learned about the circuits, yeah, circuits of the high pass and low pass filters, which consists of either RL or RC circuit, yeah, because we have learned that the order of the filter will be determined by the number of passive component, number of passive component. So basically, you must have at least L component or the inductor component or the capacitor component in your filter circuit such that you are going to have a first order filter type. Yeah. So this is what we have learned in lecture 17. Okay, in lecture 18, if you have tried to view lecture 18, so basically lecture 18 is not prepared in terms of the videos because as I mentioned in the WhatsApp message, lecture 18 is not in our syllabus. But in short, I can just explain here that in lecture 18, we are actually teach students about the higher order filters. Yeah, higher order filters means that second order filters and above. Yeah, second order and above. So for the second order type filters, we are going to have two components, at least two components of passive components. Yeah, whether it's L or C. Okay, and if you have third order of the filters, you're going to have three passive components of the circuits. Yeah. Okay, and the band pass filters and band reject filters is not considered in our syllabus because band pass filters, the lowest order for the band pass filters and the band reject filters must be the second order. Yeah, so for that, band pass filters and band reject filters will not be covered in our syllabus, but that is for your own, for your knowledge. Yeah, because later on in third year, yeah, you're going to use this in control subject. Yeah, in control subject. Okay, So let's have a look at the revision for what we have learned before. So the first one in the previous chapters, we have understand. Okay, number one, we have understand the importance of filtering. Okay, and its application in electrical engineering field. So basically, this have been learned in chapter 3, yeah, on Fourier transform, and also in chapter 5 when we learn about the Bode diagram and the type of filters. So basically, you understand about the filter in general, okay, and its application in electrical engineering. Okay, where we have learned these filters as a mean of signal filtering used in the AM modulation. Yeah, yeah. And number two, we have learned about the active and passive type of filters, but our emphasis in this course is only on the passive type. Yeah, passive type. Okay, and then number three, we have learned about the passive components. Yeah, on the filters R, L, and C. And then we have also learned about the filtering ability, the low pass filters, the high pass filters, the band pass and band reject. Yeah. And number five, we have also learned about the filters term, okay, which include the 3 dB bandwidth, I believe. Yeah, you have learned about the 3 dB cutoff frequencies. Okay, it is very important. Yeah, cutoff frequencies. The 3 dB bandwidth is basically related to the band pass. Yeah, band pass. Okay, somebody try to get in the class. Okay, let us proceed. Okay, so we also learn about the filter type, so in the filter order. So as mentioned before, our concern in this course will be only on the first order type. Okay, but I believe that you have also now understand what is meant by second order type of the filters. Yeah. Okay, and number 7, we have this is will be the main part of the main component of chapter 5, in which the Bode diagram. Yeah, you have understand well on how to use the Bode diagram in plotting the amplitude or the magnitude response and the phase response. Yeah, of the transfer function. So the knowledge of Bode diagram is very important because you're going to use this widely in the next courses in this program. Okay. So basically, Bode diagram will be very much useful when we learn about the control-based courses later on. Yeah. Okay. So once you have understand the things that we have learned in the previous chapters, so for this particular chapters, these are the things to be learned, to be covered. Number one, we're going to classify the passive filter type based on the magnitude plot. Okay. Okay. So we're going to classify the passive filter type based on the magnitude plot. So as I mentioned earlier, so two types of filters, passive filters will be covered, will be studied. The first one will be Butterworth, and the second one is Chubayev. So I hope that my pronunciation is correct. Yeah, Chubayev. Yeah. Okay. Number two, once you have understand about these filters, the second part of these lectures, we're going to learn about the parameters that will be very important, yeah, that will be very useful in the design aspects, the design steps of the Butterworth and Chubayev filters. Okay, so basically, you have to understand what are the parameters that will be required in the design process of the Butterworth and the Chubayev filters. And number 3, then only we can design the Butterworth and Chubayev filters based on the given specification. So basically, you need to be given a specification before you can design the Butterworth and also the Chubayev filters. Yeah. Okay, so we're going to see this later on, what is meant by the specification that will be very useful in the design process of the Butterworth and Chubayev filters. So this lecture 19, we will proceed, we will concentrate only on the Butterworth. So lecture 20, which will be held next Sunday, which will be our final lecture for this semester. Okay, next Sunday, you're going to cover the topics of Chubayev filters. Yeah, right. So hopefully you are clear the direction of our discussion in chapter 6. Yeah. Okay, so let us proceed with Butterworth filters. Okay, so Butterworth filters basically is produced or is invented by a British engineers named Stephen Butterworth. Yeah, so basically the filters name is after his name. Yeah, in 1930, so it's very, I mean, 80 or 90 years back. Yeah, so it's a long time ago. So this is the specific information or specific characteristics of the Butterworth filter, in which the Butterworth filter is said to have a magnetic plot. Okay, so this diagram here shows the magnetic plot of the Butterworth filter. Okay, in which it is said that the magnetic plot. Okay, so what we have here is the low pass type. Yeah, low pass type of filters. Okay, the magnetic plot is flat as possible. So this is your magnetic plot. Okay, so it is said that the plot of this magnitude is flat as possible for the pass band. Okay, as flat as possible pass band, but the roll off towards the stop band is very slow. Yeah, roll off is slow. Yeah, so this is the good things about the Butterworth filter. Okay, in which the pass band is flat, so it means that there should be less noise in the filtered signal. But in terms of the roll off, yeah, it is slow, which means that the filtering efficiency will be not that good. Yeah, not that good because of the effect of the slower roll off. Yeah, so that should be the advantage and disadvantage of this Butterworth filter. Okay, so now once you have understand about this Butterworth filter, you're going to straight away look into the design aspects of the Butterworth filter. So these are the design procedures that we're going to see for the Butterworth filters. Number one, we need to obtain, yeah, need to determine the order of the filter based on the given specification. Okay, so number one, need to obtain the order, yeah, the order of the filter, in which this order of the filter can be calculated, can be obtained if you are given the specification. Yeah, if you're given the specification, then only we can write or we can obtain the order of the filter. Okay, number two, okay, we need to obtain the cutoff frequencies. Okay, so three important things, yeah, in the Butterworth filter design. Number one, the order of the filter. Number two is the cutoff frequencies, the omega C. Okay, the cutoff frequencies. And number three will be the transfer function. So in short, we just have it as a HS. Lah. So three things to be obtained basically in the design process of the Butterworth filter. I repeat again, number one is the order. Number two is the cutoff frequencies. Number three is the transfer function of the filters. Yeah. Right. So if these are the mathematical part of this Butterworth filter, okay. So if we can, I mean, this appendix, yeah, this attachment of the filter design has been given to you. You can refer to the Google Classroom, and I provide to you the attachment related to this filter design. There are 5 pages altogether. Yeah, 5 pages altogether, which include the equations, yeah, the mathematical formulations related to the design procedures of both Butterworth filter and Chebyshev filters. Okay, so in this lecture, as I mentioned, we're going to concentrate only on the Butterworth filter. So from time to time, you can refer to the attachment, yeah, along the lectures, yeah. Right, so I'm not going to show you the attachment because I believe that you have downloaded the attachment. Okay, and within the lecture part, I mean during the lecture time, you can simply refer to this attachment if you want to have a clearer picture, yeah, on the content of the attachment. Yeah, okay, so in this discussion of the Butterworth filter, I'm going to use a low pass, yeah, low pass type of Butterworth filter as a reference, okay, as a reference, and the high pass type of Butterworth filter and also the band pass type of the Butterworth filter can be modified or can be obtained from the knowledge of the low pass design, yeah, low pass design. So this is the excerpt from the attachment. You can refer to jadwal F5, table F5, yeah, F5, sorry, table F5. in which, for examples, for this particular case, for the low pass Butterworth filter, uh, the the transformation, yeah, the transformation for your S term will be S over omega C, for instance. Yeah, for the high pass filter, the transformation will be omega C over S. And this will be for the Chebyshev that will be learned next week. Yeah. Okay, but I'm going to explain in detail after this. Yeah, but for the timing, we can understand now that our discussion for this lecture will be on low pass Butterworth. But for the high pass and other type of filters, which include the band pass and band reject, can be obtained if we refer to table F5 in your attachment. Yeah. Okay. So this is the equation for the magnitude response of the n-order low-pass Butterworth filter. Okay, so this is the magnitude response, which is actually obtained or invented by Mr. Stephen Butterworth. Yeah, so our task is just to use, just to use it. Yeah, so you don't have to memorize this. Yeah, because all the content of the attachment will be provided to you. Okay, so you don't have to memorize anything in this lecture or this chapter. So all of these information will be provided. Okay, so the HD omega, which is the magnitude response of the n order low pass Butterworth, is given by this equation. Yeah, 1 over square root of 1 plus omega over omega c to the power of 2n. And here stand for the order of the filter, and omega c here stand for the 3 dB cutoff. Yeah. Okay, so omega is your frequencies now. Okay, so basically you can refer to this equation in the first page of the attachment. So if you refer to the first page of the attachment, there are two sections. The first section is information or formulation related to Chebyshev. Okay, and the second part of this page 1 is the formulations related to the Butterworth filter. So our emphasis will be on the second part, yeah, of page 1. So you can refer to this content, yeah, of the first part of page 1, which include this formulation. And also we have this equation, which is the normalized transfer function for the n-order low-pass Butterworth filter. Yeah, so normalized transfer function is written to be HNS, and is written to be 1 over BNS, in which BNS here is your Butterworth polynomial. Yeah, Butterworth polynomial. Okay, so it means that we the transfer function of the Butterworth filter is actually depending on the Butterworth polynomial. Yeah, Butterworth polynomial. So this Butterworth polynomial is readily obtained. Okay, so you can refer again to page 5. Yeah, to page 5 of your attachment. And this Butterworth polynomial in general is given by this. Yeah, given by this equation polynomial, s to the power of n, a n minus 1, n minus 1, and so on. So all the information of these coefficients, yeah, a n minus 1, and so on, up to a1 here, can be obtained, yeah, from this table of Butterworth polynomial. Okay. Okay, so let's have a look at the second page now, this next page now. Okay, so the design of the Butterworth filter, as I mentioned before, will be depending on the Butterworth polynomial, the BNS, because from the previous page, we have understood that the normalized transfer function is given by 1 over Bn of S, okay, right? And the Bn of S, the Butterworth polynomial, as I mentioned, can be obtained from table F6a or table F6b. Okay, so both are the same, yeah, both are the same, but just different in terms of the arrangement of this information, yeah. Okay, so for instance, I give you an example. If you refer to the third order, yeah, third order means that the n is equals to 3. Okay, n equals to 3. So if we refer to the Butterworth polynomial table, F6a or F6b, you can have a look that for n equals to 3, your Bn polynomial is given by this. Yeah, which is the B3 of S is S plus 1 multiplied with S squared plus S plus 1. So this is the equation, yeah, I mean the Butterworth polynomial for the order n equals to 3 for the Butterworth polynomial, yeah. Okay then. All right. So I hope by now you understand about these Butterworth filters and its relationship with the Butterworth polynomial. Okay, in which we need to obtain, the transfer function of the Butterworth filter will be heavily depending on your Butterworth polynomial. Okay, all right. Okay, so as I mentioned earlier, in order for us to obtain the filter order, yeah, filter order, because if you want to calculate the transfer function of the filter, you need to actually know what should be the order of the filter. Because once you know the order of the filter, then only you can use the appropriate Butterworth polynomial. Am I right? Yeah. So if you, let's say, based on the design specification, you manage to get that the filter order is equals to 4. So then you can refer to the table F6A or table F6B, and from there you can calculate or you can obtain what should be the B4 of S, or the Butterworth polynomial equation for the n equals to 4, or order equals to 4. Yeah. So then only you can find what should be the normalized transfer function of H4 of S. Yeah. So first thing first, you need to obtain the filter order of the Butterworth filter. Yeah. Okay. So this is the determination or calculation of the filter order, right? So you can refer to the page 1 of the attachment, which can give us the information about the equation 1 to 7 in this slide and the next slide. Okay, so we have 7 equations altogether for this slide and next slide. So all of these equations 1 to 7 will be the important equations or crucial equations that shall be applied in the design of the Butterworth filters. Yeah. Okay, so you can refer to page 1 of the attachment. You can refer to the attachment if you have it with you now. Okay, so the first equation will be the alpha. Yeah, alpha is your gain. Yeah, gain, which is given by 20 log of a j omega in a dB. Yeah, alpha in dB, gain in dB, and it should be then equals to negative 10 log of 1 plus omega over omega c to the power of 2n. So basically this alpha is based on the previous equations of this hj omega. Yeah, so this is in linear form. Yeah, in linear form. So in dB is 20 log of this value. So that's why we have the value of alpha in equation number 1. Yeah, you can refer to the table. Yeah. Okay, so from this equation number 1, you can have two distinct value of gain, because we know that, okay, we are referring to the low pass filters. Yeah, so for low pass filters, we have two distinct regions. The first region here is the pass band. Yeah, so we have a pass band region, and we also have the stop band region. Yeah, okay, this is understood lah. Yeah, from what we have done in the previous chapter 5. Yeah. Okay, so for the pass band, there are two important parameters, which are the alpha p, which will be the pass band gain. Okay, so I can write here, this is a pass band gain. Okay, and we also have the omega p, which is the pass band frequency. Okay, so we can refer to this diagram here, relationship between this diagram, the amplitude diagram, or the amplitude plot of your low pass filter Butterworth. So the alpha p, so this is your omega p, omega p. Yeah, omega p is the pass band frequencies, and you have this relationship with the alpha p. Yeah, should be alpha p there, which is the pass band gain. Okay, so we also have the stop band gain, the stop band frequencies. Yeah, omega alpha s will be the stop band gain. Okay, stop band gain, and omega s will be the stop band frequency. Yeah. Okay, so if we refer to this, we can have omega s, and if we have the information about the alpha s, which is your stop band frequency. So you need to be given these 4 informations, yeah, in order for you to design the Butterworth filter. So these 4 informations are the alpha p and omega p, which are respectively the pass band gain and the pass band frequencies, and also the alpha s and omega s, which are the stop band gain and stop band frequencies respectively. Yeah. Okay. So from here, we can have informations about your alpha p, which can be calculated. Yeah, calculated based on equation number 1, in which we just substitute alpha as alpha p and omega equals to omega p. Okay, so that will enable us to find the alpha p. And then from equation number 1, we can also substitute the alpha to be alpha s and omega to be equals to omega s, which will result in equation number 3. Okay, so equation number 2 related to the pass band region. Equation number 3 is related to the stop band region. Okay, so we have equation number 2 and equation number 3, which are actually obtained from equation number 1. Yeah. Okay. So you can stop me any time if you want to ask any questions, yeah, related to this lecture. Okay, then from equation number 2 and equation number 3 that we have obtained, yeah, in this slide, we can then obtain equation number 4. Yeah, equation number 4, in which this is a ratio of omega s over omega p. Okay, you can have it from this equation number 2 and 3 by manipulation. You can have equation 4, so you can refer to equation 4 in your attachment, page 1. Okay, and from this equation 4, you can obtain the n. Yeah, you can obtain the n in which you can have it to be equal to this equation. Okay, n will be equal to log, okay, tan of alpha s over tan minus 1 divided by tan alpha p divided by tan minus 1 divided by 2 log of omega sn. Okay, so these are the things to be known basically. So omega sn here will be depending on your filter type. So if you refer to page 2, yeah, page 2 of our attachment, you can have a formulation for the omega sn, in which for a low pass filter, omega sn, this is for the Butterworth, yeah, for low pass filter Butterworth, omega sn is written to be omega s over omega p, whereas for the high pass filter, omega sn is omega p divided by omega s. Okay, so for our case here, since we in this lecture, our emphasis or our discussion is on the low pass Butterworth filter. So for that particular case, our omega sn in this equation 5 will be omega s over omega p, which is for the low pass Butterworth filter. Yeah. Okay. All right. So then, yeah, we can calculate. Yeah, we can have two values of cutoff frequencies. Okay, in which from equation 2 and 3 again, yeah, equation 2 and 3, if we manipulate this equation 2 can be written in terms of this equation 6. Yeah, so if I can write for you, this is from equation 2 and this equation 7 is from equation number 3. Okay, so basically we can have two values of cutoff frequencies. The first cutoff frequency is equation 6 is to be based on information of parameters of passband region, which include the omega p and the alpha p. Okay, whereas the second cutoff frequencies, which is from equation 7, is obtained from information of stop band region information, which are the stop band frequencies and the stop band gain. Okay, so we're going to have two values of cutoff frequencies. I repeat again, two values of cutoff frequencies. Yeah, we have n can be obtained from the previous equation 5. So when we have equation 5, we can substitute into equation 6 and 7. Okay, so from 6 and 7, we are going to have two values of cutoff frequencies. The first cutoff frequencies is to be based on passband information, and the second cutoff frequencies is obtained from the stop band information. Yeah. Okay. Right. So hopefully by now you have understand this discussion about our Butterworth filters. So again, I repeat again, that all these equations 1 to 7 that have been discussed in this slide and the previous slide can be referred to page 1 of our attachment. Yeah. Okay, so these are the steps that will be required in our design process of a low-pass Butterworth filter. Okay, number 1 is to calculate the order of the filter by applying equation number 5, which is this equation that we have seen earlier. Yeah, so equation number 5 will give us the information about the n. So need to calculate the n, in which you have to substitute all the informations given from the given specification, the alpha s, the alpha p, omega s, and omega p. So you need to have these 4 informations for us to calculate the filter order n. Yeah, so this information alpha s, alpha p, omega s, and omega p will be given either in a numerical value or in a graphical value. Means that if the numerical value is not given, you have to refer to the graph. Yeah, to the graph that should be given. Yeah, should be given. Yeah, right then. So these are the 4 parameters that will be very important, or that will be very useful in calculating the filter order n. So once you have these 4 information, then only you can calculate the filter order n. Okay, so one thing to be remembered here is that if your calculation of the n, let's say the value obtained is 1.7, so you need to round it up to, so if the value is 1.2, you have to round it up also to 2. And if we have, let's say, 3.45, also you need to round it up to 4. Okay, so I hope by now you have understand how to round up the rounding up the n value. You know, as long as the value is bigger than, let's say we have 2.3, so it should be now written n to be equals to 3. And let's say you have 2.1, also you need to have you need to put n to be equals to 3. Yeah, so that's how you rounding up the value of the filter order n. Okay. Right, so that's the first step. The second step of design process is to calculate the actual cutoff frequencies. So this is the things to be obtained, right? So as I mentioned earlier in these lectures, in designing a Butterworth filter, there are 3 informations to be obtained. The first one is the filter order. The second one is the cutoff frequencies. And the third one is your transfer function. So the first step has been done, which is the filter order. The second step is to calculate the cutoff frequencies. Okay, so as what we have learned in previous slide, we have 2 equations, 6 and 7, to calculate the cutoff frequencies. Yeah, so equation 6, which is to be based on the passband information, which are alpha p and omega p. We are going to have the first cutoff. Let's say I write this as omega c1. Okay, and from equation 7, we are supposed to get, or we are supposed to use information from the stop band region, which are the alpha s and omega s information. Yes, stop band gain and stop band frequencies. And from here, you should be able to find the second cutoff, which is the omega c2. Yeah, second cutoff, which is the omega c2. So these are, sorry, yeah, I need I need to erase this line here. Okay, right. So yeah, so we're going to have 2 cutoff frequencies here from 6 and 7. Okay, so but we need to choose only one out of these 2. We need to choose only one. Yeah, in which these are the rule of thumb that need to be used. Yeah, so basically, once you obtain this omega c1 and omega c2, so you are going to use these cutoff frequencies values to calculate the passband gain, the alpha p, and the stop band gain alpha s using equation 2 and equation 3. So if I can refer back to the previous slide, this is the one, equation 2, okay, and equation 3. Okay, these are the equations that shall be used in calculating the alpha p and the alpha s. Okay. So basically, if I can sketch something here. So from omega c1, from the equation 6, we are supposed to get alpha p1 and alpha s1, Whereas for omega C2, we are supposed to get alpha P2 and alpha S2. So we have two pairs, yeah, from omega C. Yeah, we have two pairs of alpha P and alpha S. Okay, so once you have these two pairs of alpha P and alpha S, you need to choose. Yeah, you need to choose which of these cutoff frequencies, whether it's omega C1 or omega C2, that will give us this ability. Okay, the first one is that the calculated alpha P, yeah, this calculated alpha P, whether it's alpha P1 or, sorry. Okay. Okay, so you have two alpha P's, yeah, whether it's alpha P1 or alpha P2, okay. So this alpha P1 or alpha P2, the value of it must be greater than the given spec of alpha P. Yeah, because previously you should be given a specification, right? Yeah, before, remember, in order for us to calculate the filter order n, you must have been given the alpha P, the alpha S, omega S, and omega P. So these are the specification given, yeah, earlier. Okay, so for the step number 2, your calculated alpha P is the alpha P1 or alpha P2, which is obtained or which are obtained from the use of omega C1 or omega C2. Okay, so the value of alpha P's here must be bigger than the given specification. Yeah, and the second condition is that the calculated alpha S, whether it is alpha S1 or alpha S2, the value of it must be always smaller than the given spec. Yeah, this specification of alpha S must be smaller than that. Okay, so you have to choose which pair. Yeah, which pair? Either pair of alpha P1 or alpha S1, or pair of alpha P2 or alpha S2 that will satisfy these conditions. Okay, so the pair which satisfy this condition, so its omega C1 shall be selected. For instance, yeah, for instance, if from the calculation later on we find out that, okay, so alpha P1 and alpha S1 do satisfy this condition, so for that particular case, our selection of cutoff frequencies will be the omega C1. Okay, so that's how we select, that's how we choose the cutoff frequencies. Okay, hopefully after this we are going to have few examples. So from these examples, I'm hoping that you can understand these issues of selecting the cutoff frequencies. Yeah. Okay. So number 3 is to obtain the normalized transfer function. Okay. So this is to be based on the use of the Butterworth polynomial, in which we have calculated earlier that H and S, yeah, shall be equals to 1 over B and S. Okay. So the B and S, the Butterworth polynomial, will be depending on the order of the filter of n. Okay. So if we refer to the table of page number 5, yeah, I mentioned before, table F6A and table F6B, you can then calculate, or you can then obtain what should be your Butterworth polynomial. Yeah, depending on the n, or depending on the order of the filter. Then only you can calculate what should be your normalized transfer function. But this is yet to be the answer, because we want to find the actual transfer function. What we have here is normalized transfer function, in which this is for the case of omega C equals to 1. Okay, so for the actual transfer function, okay, so what you have to do is that you have to substitute the S component or the S value of your normalized transfer function terms, yeah, into S over omega C, yeah, because we are referring to low pass, yeah, low pass Butterworth filter. So that's why our S is substituted with S over omega C. But if your filter is a high pass type, I'm referring again to this table F5, okay, if your filter is a high pass type, so your S term here need to be substituted with omega C divided by S for the case of Butterworth. So this is for the case of Chebyshev, which will be learned later, yeah, on Sunday. Okay, so because we are dealing with a low pass Butterworth filter, that is why for the Butterworth filter low pass, the S will be then substituted by S over omega C. And if your filter is a high pass type, the S shall be then substituted by omega C divided by S. Okay, for instance, yeah, so I give you a very simple example. For instance, if your let's say H3S equals to 1 over S power of 3 plus 2S power of 2 plus 2S plus 1. Okay, so this is your normalized transfer function. So along the way, you manage to get that the cutoff frequency omega C, let's say equals to 15.7, for instance, radian per second. So from here, you can write that the Hs, which is the actual transfer function, shall be 1 over S divided by 15.7 power of 3 plus 2. S over 15.7 power of 2 plus 2 S over 15.7 plus 1. Okay, this is for the case of low pass Butterworth filter. If the case of high pass, these terms of S over 15.7 need to be the other way around, which will be 15.7 divided by S power of 3 and so on. Okay, so that's how we calculate the transfer function for the Butterworth filter, which will be depending on the filter order and also the cutoff frequencies which have been obtained from step 1 and step 2 of the design process respectively. Yeah. Okay, hopefully you understand clearly on this flow of design process of low pass Butterworth filter. Okay, so let's proceed with the examples of this Butterworth filter. Okay, number 1 is to calculate the order of the Butterworth filter with the following specification. Okay, so as mentioned before, you need to be given these parameters of the Butterworth filter before you can obtain the order. Yeah, we need to be given the omega p, which is the passband gain, passband frequencies, omega s, which is the stop band frequencies, alpha p, which is the passband gain, and stop band gain of alpha s. Okay, we substitute all of these 4 parameters in the equations here. Okay, so we refer to this, we have alpha p and alpha s is negative, right? So in your calculation of n, we need to use alpha s to be positive value all the time, yeah? So that should be a 20 dB, and the alpha b will be a 0.5 dB. So we ignore the negative sign, yeah? We ignore the negative sign, yeah? So then you have to substitute the positive value only on these equations. Okay, so n, because of low pass filter, so omega Sn is omega s over omega p. So omega s here is equals to 200, and omega p is 100. So we have 200 over 100, which is equals to 2. Yeah. So end up, when we use the calculator, supposedly you're going to have n of 4.8, and rounding up, you're going to have n equals to 5. Okay. So that's how you calculate the filter order n based on the given formulations. Yeah. Okay. I hope you understand. Yeah, you understand clearly about these examples on the filter order calculation. Yeah, for the Butterworth filter. Okay, so let's have a look at this example. Number 2. We need to design a Butterworth low pass filter. Yeah, low pass Butterworth filter, in which we are given a passband information, number 1. Okay, so this first information is for passband, yeah, passband region, and the second information is for stop band region. Okay, for the passband information, the passband gain is between 1 and 0.891 or negative 1 dB gain for omega between 0 and 10. Okay, so if I can sketch this passband region for you, okay, so this is your omega, so this is your Hg omega amplitude in dB, okay, I got it in dB. So that should be the passband gain because we are referring to the low pass filters. So this is 0 dB. Yeah, the passband is between 0 dB because 1 is 0 dB, yeah, in linear is 1. So in dB will be 0 dB, and 0.819, which is in linear scale, so in dB will be negative 1 dB. So negative 1 dB should be there, and it is from 0 to 10. So it means that the passband is between 0 and 10 radian per second. Yeah, so that should be the passband region. Whereas for the stop band region, it is not to exceed a negative 30 dB gain for omega bigger than 20. So it means that the stop band region should be there. Okay, so that should be 20 radian per second, and your stop band gain will be negative 30 dB. Okay, so that should be the plot, yeah? The plot of your magnetic response, supposedly, for the given Butterworth low-pass filter, yeah? Okay, so from here, from this information, you have alpha P equals to negative 1 dB, omega P equals to 10 radian per second. Your alpha S will be equals to negative 30 dB, whereas your omega S equals to 20 radian per second. So this is based on the given information, yeah? Sorry. Need to resketch this for you. So that should be the line. Okay, should be radian second. That should be negative 30, yeah? Okay, so hopefully you are clear about this sketching. Okay, that should be your omega S, yeah? Right. Okay, so hopefully you are clear about the information in this question. So basically, when we have this kind of problems, you need to, you must be able to extract, yeah, must be able to extract the information of these four parameters. Hello, any question? Hello.
I want to ask why it gain between 1 and 0.891 is 0 dB and negative 1. I don't understand that part.
Is it for this particular case? Okay, this is a linear scale. So how to change from linear to dB? How to change from linear to dB?
Using the formula, is it?
20 log of the values of linears, right?
Okay.
Alright,
Yeah.
okay, good.
Yeah,
So we're going to have 20 log 1 with 0 dB, 20 log 0.811 will be negative 1 dB. Again, for this 20 log of 0.0316 will give us negative 30 dB, yeah? Okay, so I hope you have understand this line. Maybe you forgot about that. The change or transformation from a linear scale to a dB scale. Okay, right. Number one, calculate the order n of the filters. Okay, that should be the first question. Number two is to sketch the magnetic response of this filter. So basically, we have done the second question. Basically, that should be the sketch of your magnetic response. Okay. Number three is to determine the normalized transfer function, HNS, and number four is to determine the actual transfer function. So these are the things that need to be obtained from the from this problem. Okay, number two has been answered. Okay, so I think it's clearly shown here on the magnetic response of your low pass Butterworth filters. Okay, for the calculation of the order of the filter n, so this to be based on equation number 5 that we have seen earlier. So let us proceed with the solution now. Okay, so all right, so we have done, yeah, we have resketched this for you, yeah. So that should be your the sketching of your low pass Butterworth filter. Okay, so hopefully you will understand clearly on this sketching, right? So these are the equations that will be very useful along the way, yeah, along the way of process of solving these problems. We have alpha P equation and we have alpha S equations, yeah, right. So these will be the equations used to calculate the n. Sorry, I need to erase this line here. Sorry for that. Okay, for that, yeah. Right then, so we have the n based on this equation. So substituting the alpha S, which is equals to negative 30, or since we have a positive only, yeah, so use a positive value only, so 30 dB, alpha P will be equals to 1 dB, not a negative sign. So omega Sn will be omega S over omega P, which should be 20 radian per second divided by 10 radian per second. So by having all of these four informations, you are going to get that the n will be equals to 5.95, which rounding it up, we're going to have n will be equals to 6. Okay, yeah? So that should be your filter order of the given specification. All right, yeah, it's straightforward only. We just substitute the parameters alpha S, omega S, alpha P, and omega P in your equation number 5 to calculate the N, yeah? Okay, that's done. Okay, number 2, which is the sketching, have been done here, shown here, so it'll be okay. Then we'll be calculating the, okay, if I can recall back, it is to obtain the transfer function. Okay, so to find the transfer function, you need to calculate the cutoff frequencies. Yeah, before you can calculate the transfer function, you need to calculate first the cutoff frequency. So these are the steps that have been explained in step 2, yeah, in our lecture before. So to determine omega C, we have 2 equations to be used, yeah. Okay, that should be the first equation, which is to be based on the usage of omega P and alpha P. Okay, so we are having omega P here equals to 10 and alpha P here equals to 1 dB. So you substitute 1 as alpha P and N here should be equals to 6, yeah? Right, so that should be the first values of your cutoff omega C. The second cutoff frequencies omega C is to be obtained based on omega S, which is equals to 20, and alpha S, which is equals to negative 30 dB, but you just simply use 30 here as positive value. And again, N here will be equals to 6, yeah, based on the N value which has been calculated earlier. Okay, so by substituting all of these information, omega P, alpha P, omega S, alpha S together with the N, so we are supposed to get this value of omega C's, yeah? So there should be 2 values of omega C. The first one is 11.192 from passband information, and the second cutoff frequencies is 11.247 from the stop band equation. Okay, yeah? So we are supposed to get 2 cutoff frequencies. Okay, and then this will be the rule of thumb in selecting which cutoff frequencies shall be adopted. Yeah, which omega C's shall be adopted, in which the omega C's need to fulfill this rule of thumb. Okay, so these omega C's shall be used to calculate the alpha P, alpha S. So I just use as alpha P1 and alpha S1, and these omega C's will be used to calculate the alpha P2 and alpha S2. So we are supposed to get 2 pairs of alpha P and alpha S, since we have 2 values of omega C, yeah? All right, so if you can recall back, the omega C's here need to be, okay, the alpha P and alpha S are calculated based on equation 2 and equation number 3. Okay, all right, so from here, yeah, once you have these omega C's, when you have omega C of 11.192, you are supposed to get, yeah, you are supposed to get the alpha P. Yeah, you can calculate this on your own, yeah. The first alpha P calculated from 11.192. So I believe that this is to be based on equation number 2 that enables us to calculate the alpha P. Yeah, if I can recall back from your table. Sorry, yeah. Wait for that. Okay. You're going to have the alpha P, which will be equals to 0.892. And again, from the same alpha, from the same omega C, you are going to get the alpha S, which is obtained from equation number 3 of 0.03069. Okay, yeah. All right. Hopefully you understand about this, yeah. Okay, so from equation number 2, if I can clarify this further. From equation number 2, in calculating the alpha P, yes, so that should be the subject, right? Omega alpha P equals to something. Okay, for the right-hand side, you need to use your omega C of this, 11.192, okay? And your omega P is used based on the given specification, which is 10 radian per second, yeah? The same thing is applied from equation number 3 in calculating the alpha S, okay? You have the right-hand side having the information of omega C, which is 11.192, and your omega p should be equals to 10. Okay, so that's how you're going to get the alpha p and alpha s from equation 2 and equation 3 respectively. Okay, and then from the second, for the second omega c, which is 11.247, again, by using equation number 3, you're going to get alpha s, which is 0.032, and by using equation number 2, yeah, you're going to get the alpha p of 0.8996. Okay, so from here, you have to select which omega c that should be used. For the first omega c, the calculated alpha p, yeah, this is calculated alpha p is bigger than the given specification. And for the calculated alpha s is smaller than the given specification. So basically, we can have a look that for omega c of 11.192, it satisfies these conditions. Yeah, calculated alpha p is bigger than the given specification, and calculated alpha s is smaller than the given specification. Yeah. Whereas for the second omega c, which is 11.247, the calculated alpha s is bigger. Okay, so from here itself, from the first value of alpha s itself for omega c of 11.247, the calculated alpha s is bigger than the given specification, in which it shows that this does not follow the conditions in which the calculated alpha s must be smaller than the specifications given. Yeah. So although it fulfilled the alpha p condition, but it failed with the alpha s condition. So by right, we can have this condition that the only omega c's, the omega c's that satisfy both of these conditions will be 11.192. Okay, so that's why we choose the omega c in this case of 11.192. Yeah. Okay, hopefully you have, you clearly understood this method, yeah, the way, the process of calculating the cutoff frequencies here, yeah. Okay, so let us proceed further with calculation of the transfer function. So first, we need to calculate the normalized transfer function, the HNS, and from the previous step number 1, we have calculated that the filter order n equals to 6. So based on that, you need to choose the binomial, the polynomial Butterworth for n equals to 6. So that should be the case. You have to choose n equals to 6, yeah, in which the bn shall be equals to d. So if you can write for you, the bn, which is the Butterworth polynomial, okay, n should be now equals to 6, yeah, b6 should be s power of 6 plus 3.8637, I'm using this one, yeah, s power of 5, plus, I'm using the second one here, which is for A4, 7.4641, yeah, 4641, s power of 4, plus, yeah, A3, 9.1416 s power of 3, okay, A2, 7.4641 s power of 2, plus A1, 3.8637s plus 1. Okay, so that should be your Butterworth polynomial for n equals to 6. Okay, so the normalized transfer function, which is hn or h6 of s, shall be equals to 1 over b6 of s. So simply we just substitute this b6s down here to be h6 of s. Yeah. Okay, so the same things apply for other Butterworth polynomial. So let's say if your n equals to 5, so you have to refer to n equals to 5, and that's how you obtain the Butterworth polynomial terms. Yeah. All right. Hopefully you are clear about this. Yeah. Step number 3. And finally, okay, this is the one I mentioned before. You have this hn of s for n equals to 6. Okay, and finally, for us to calculate the actual transfer function for low pass Butterworth filter, we are using this table F5, yeah, in page number 2, if not mistaken. You can refer to page number 2. Yeah, you have this. Page 4, I believe. Page number 4. Okay, so low pass Butterworth filter. This has been informed earlier. you have to transform the S into S over omega C. So we have calculated earlier that omega C equals to 11.192. Yeah, from the previous step, you can then calculate that the HS, the actual transfer function for the given specification of low pass filter Butterworth will be equals to this. Yeah, so all the S terms shall be now substituted to be S over the omega C. So that should be the answer for your transfer function of the Butterworth filter low pass type. Okay then. Yeah, hopefully you understand clearly on this example. Yeah. Okay, we proceed with the next example, which will be the last example for today's lecture. Okay, so this has been given in terms of the magnitude response. Okay, again, we are referring to low pass type of Butterworth filter. Okay, in this information, you are given the specification, a low pass Butterworth filter. The passband gain is between 0 dB and negative 2.5 dB for the frequency range of omega from 0 to 15, which means that the passband gain is between 0 to negative 2.5 dB, which means that our alpha P is negative 2.5 dB. Okay, sorry for this interruption, yeah, this line. I'm sorry about this. Okay, need to rewrite again. So alpha P is a negative 2.5 dB. Okay, and the omega P, based on this information, it should be 15 radian per second. Okay, whereas for the stop band gain, it is negative 22 dB for frequency bigger than 30, which means that the alpha S of negative 22 dB and your omega S of 30 radian per second. Yeah, so these are the informations obtained from the questions. Yeah. So from here, you need to design the low pass Butterworth filter. So the design means you have to find the order of the filter, need to find the cutoff frequencies, and need to find the transfer function. That's what we mean by a design of a low pass or design of a Butterworth filter. Lah. Okay. For the high pass should be the same, yeah? High pass should be the same. You need to find the N, need to find the omega C, need to find the HS, but the difference only on the substitution or transformation of your S. Remember, if a low pass is S over omega C, but for high pass, it is omega C over S. That should be the only difference between the high pass and the low pass Butterworth filter, yeah? But the flow of design should be the same. Obtain the N first, obtain the cutoff frequencies, and obtain the HS. Okay, right. So that should be the steps. Let us proceed with the calculation of the filter order, and I believe that you can try to do this on your own. So the N should be obtained of 4. You're going to get N equals to 4. You can try this on your own. Again, ignore the negative sign for the gain. Yeah, means that in calculating the N, all negative sign for the alpha P and alpha S shall be ignored. Okay. Step number 2, these are the process of calculating the cutoff frequencies. So again, we follow the things that we have learned in the previous example. We are supposed to get two values of cutoff, 11.47, 15.47 and 15.94. So by using the rule of thumb, you can prove this on your own that the answer or the selected omega C will be 15.47. Yeah, you have to prove this on your own. Yeah. And from here, you are going to get the, you have obtained the N equals to 4. So by using the table of Butterworth polynomial, you're going to get that the B4 will be equals to this. Yeah, that should be your Butterworth polynomial. And subsequently, you can find the normalized transfer function of 1 over B4 of S. And finally, the actual transfer function HS will be simply 1 over all the S terms just now shall be divided by the omega C. Yeah, so that's how you obtain the transfer function for the given specification of low pass Butterworth filter. Okay then. Okay, so that's all for lecture 19. Okay, so I hope that you have understand this topic of Butterworth filter design clearly. Okay, and we're going to proceed with Cebaca filters, the process of designing Cebaca filters in our lecture 20, which will be held on next Sunday, which will be our last or final lecture for this semester. Okay then, any more questions related to this lecture 19 before we end the class